Well, good afternoon. It's 12:19. We're 4 minutes late getting started for Calculus 3. This is on 7th of November 2018. I'm the only one in the room right now. Don't know where everybody is. But before we get started where we left off last time, let me go over just a couple of minor things. Number one, I can't remember if I said this to you before, but I'll say it now in case I didn't. I am getting caught up very slowly, but getting caught up in my grading. I finally did get the spring schedule, I thought, finished, but a couple of people have made a couple of requests to have changes made, so I have just a couple of other minor changes to make in spring schedule. That shouldn't take long. I'll either get it done today, tomorrow, or Friday. That's not a big deal. Maybe one of them today and the other wait till Friday, I don't know. But, so I have got back to doing grading again. I haven't gotten to this class. There aren't but a couple things to grade, but I will be there fairly soon, I think. I've got one big class that has a lab, and we have a lab just about every time we meet. We meet twice a week, and then they've had 2 tests. So I have bunches of labs, and it's a big class, 27, 28 students in it. So I've got just a ton of grading to do for that one. And then for the other classes, I'm a little more caught up. So anyway, I hope to be able to get caught up on grading, if not by Friday, hopefully by the weekend. We'll just see how things go. I've got a couple of things I have to take care of this weekend that I know I won't have lots of time for grading, but I will have some time. Okay, the other thing, and this is, again, a fairly minor thing, normally on Tuesday and Thursday, including tomorrow, I would have office hours from 11:15 to 3:15. However, tomorrow they've called the faculty meeting, and that will be starting at 2:30. So I'm going to have to leave the office well before 2:30. It's fortunately on this campus, so I'll be leaving 2:20, 2:25, something like that, to go to the Ethel Hall building for the faculty meeting. And then I won't be there that long because I've got a class starting at 3:15. And it's a mini-term 2 class, so we can't afford to miss a big chunk of class because every class is like a week's worth of material. So I will be out of the office from, say, 2:20, 2:25 until 3:15, or close to 3:15. I need to get back and get set up for class at 3:15. So tomorrow's office hours are cut just a little bit, maybe 45, 50 minutes off my office hours tomorrow. Okay, other than that, I can't think of anything else. No one else has come in, so let's go on and pick up where we left off last time. Chapter 13 is functions of several variables, and 13.6, directional derivatives and gradients. And this part of this chapter, of the section, is dealing with functions in 3 variables. Okay? So we got up to this last time. Let's talk about the directional derivatives and gradients in 3 variables. So let f be some function in 3 variables, independent variables, x, y, and z, with continuous first partial derivatives. Each of those 3 variables have continuous first partial derivatives of that function f. Let's see. The derivatives, first partial derivatives of those 3 functions are continuous. Okay. The directional derivative of f in the direction of some unit vector u, which we'll just call a, I plus bj plus ck, but it needs to be a unit vector, is given by, and the directional derivative in the direction of that vector u, unit vector u, of the function f of x, y, z, would then be the a, the coefficient of the I thing, times the first partial of f with respect to x, plus the b, the j component of u, times the partial of f with respect to y, plus c, which is the coordinate of the unit vector in the k direction, the z direction, times the partial z with respect to partial f with respect to z at x, y, and z. Now, as just looking at that, it pretty much, I mean, this is exactly it. That is that unit vector dot product with the gradient. Though they're not saying that yet, but they will in a minute. Okay? Yeah, it's coming up really soon. The gradient of f is defined, of course. Gradient is a vector quantity, remember, of a scalar function scalar function f of independent variables x, y, and z would be the partial of f with respect to x in the I direction, the partial f with respect to y in the j direction, and the partial plus the partial z f with respect to z in the k direction. So the properties of the gradient are as follows, and this is what I just noted above. The directional derivative in the direction of the unit vector u of the scalar function f of x, y, z would be the dot product of the gradient of f at x, y, z with its unit vector, the one that you want in that direction. Okay, secondly, if the gradient of f, x, y, z is the zero vector, then the directional derivative with respect to the direction u is also zero for all u, for whatever u you would happen to choose, because it's dotted with the gradient, and if the gradient is zero, the dot product is zero. Okay? The direction of maximum increase of f is given by the gradient. Seems like that would be the first statement to make, and then make all these others, but they do it this way. The maximum value of the directional derivative of f of x, y, z would be the magnitude of the gradient. Oh yeah, okay. The maximum value of the directional derivative in the direction of u with the gradient would be the magnitude of, directional derivative of the function f would be the magnitude of the gradient. That would be the maximum value of d sub u. And the direction of the minimum value would be exactly the opposite of that, in the direction of negative del f, the gradient of f with respect to x, y, and z as a function of x, y, and z. The minimum value of the directional derivative in the direction of u of the function f of x, y, z would be minus the opposite direction. The minimum value would be the opposite of the magnitude of the gradient of f, negative of that. Okay. Here's example 8. Sorry, I've had so much drainage today. One of the students said it's probably with the weather changes, and it could be, I don't know. Said find the gradient of f of x, y, z for this function f of x, y, z equal to x squared plus y squared minus 4z. So the gradient would be, let me get my pen set up. That gradient is, and that's a vector quantity, would be 2x, the partial of f with respect to x, so 2x in the I direction, plus 2y in the j direction, minus 4 in the z direction. Whoops, in the k direction. Sorry about that. I wanted to write for z, but that is not. Let me see if I can correct this a little bit. I can't get my eraser to come up. There it goes. Okay. Minus 4 in the k direction. Okay. So there's the gradient. That's the first part, grad f for that function. Find the direction of maximum increase of f at the point 2, negative 1, 1. Find the direction of maximum increase at the point 2, 1, 1, 2, negative 1, 1. Well, the direction of maximum increase is in the direction of the gradient, okay? And so you just plug in those two values in the gradient. So this would be the gradient at 2, negative 1, 1. And that would be 2 times 2 is 4. For I minus 2j minus 4k. So there's the direction of the maximum increase. That would be in the direction of that. Now, sometimes when they say direction, they mean the direction of the, in terms of the unit vector. So I'm not sure that's what they're expressing here. It would be in that direction of the gradient. If you want it expressed as a unit vector, let's see what they're going to do next. 4i minus 2j minus 4k. Oh, that's it. That's all they wanted. Okay. So they don't want the unit vector, just the gradient vector. And that ends 13.6. Homework exercises here would be either 3 or 5 or both. They're both at calcchat.com, 3's at calcview. Either 7 or 9 or both. They're both at calcchat, 7's at calcview. Either 11 or 13, they're both at calcchat. Any of the odds 15 to 19, they're all at calcchat, 17's at calcview. Either 21 or 23, they're both at calcchat. Either 25 or 27, they're both at calcchat, 25's at calcview. Any of the odds 29 to 37, they're all at calcchat, not one at calcview. Sorry, I'm having drainage problems and my throat's getting clogged up. Do either 39 or 41 or both. They're both at calcchat. 41's at calcview. Do either 43 or 45 or both. They're both at calcchat. And then do 47, 49. If you want to think about it, the 47 or 49, if you want to go a little deeper, 51's are think about it problems under exploring the concept. Now, there is an area of mathematics called topography. I thought at first this was what it's doing. This is talking about geological topography. Number 53 deals with that. There's a temperature problem, 55. Those both should be at calcchat. 57 should be at calcchat and is at calcview. 59's at both. 61 and 63 are true-false problems that should be at calcchat. And 65 is a problem you could have, you'll find it calcchat as well. as is 67. Okay. Now, one reason I paused right there, I don't know if you could pick it up on the microphone, but there was a big, loud clap of thunder. We had been having some rain, and now it seems like the thunderstorm is starting. Usually the thunderstorm starts and then rain follows, but this is sort of doing in reverse order. So anyway, that's finishes 13.6. So let's see if there's any more slides. Oh, sorry, I forgot. No. I just hit the wrong thing. I meant to clear my writing, and it's not clearing. So I can't show you what they do for their... I'm going to see what keeping this does. I don't think it's what I want it to do. No, it isn't. Let me go back to current slide. Okay. So the gradient is that, which is 2x plus 2y minus 4k. Follows that the direction of maximum increase would be in that direction. Okay. The direction of maximum increase would then be plugging in at the point 2, -1, 1 would be plug those values into your gradient. You get 4i minus 2j minus k. They show the figure here, which is also in the book, and that direction of maximum increase. Notice you've got a three-dimensional object, and the direction of maximum increase seems to not be any, it's on the surface but pointing away from the surface, which, you know, in some senses seems a little counterintuitive, but you have to almost imagine a fourth dimension that would be the direction in which this thing would be increasing. Okay, not a very satisfying description. All right, let me get out of here. Not what I want. That's what I want. Okay, so let's move on to 13.7. I sort of feel like I'm in slow motion. My head is so clogged up. And like the student said, I wonder if it is a change of weather, because you can tell there's some pressure differences, or I suspect there are, going on out there. So let's go get the slideshow set up from this slide. We're still in Chapter 13, Functions of Several Variables. In this section, 13.7, we're looking at tangent planes and normal lines. Okay. So our first objective is to find the equations of tangent planes and normal lines to surfaces. We'll find the angle of inclination of a plane in space. Okay. How in the world do you define that anyway? And we'll compare the gradients of a function in 2 dimensions and a gradient of a function in 3 dimensions. And I guess for some reason they capitalized the F on the second, not on the first. We'll see. So let's, sorry, let's go, so sorry. Look at tangent planes and normal lines to a surface. All right. Now, in general, we've represented surfaces in space primarily by equations of the form z is equal to some f of x, y. where z is your dependent dimension, you might say, and f and x, y are x and y are your independent variables that determine, when you do apply them with the function f, what the values of z are. Okay, so that would represent a surface in space, and f of x, y would represent that, and that would represent the country z. Okay. In the development to follow, however, goodness gracious, it is convenient to use a more general representation, and this is your capital F. The capital F of x, y, z equals 0, rather than z, the dependent variable, equals some function of x and y. Thank you for being here. It's so boring talking to myself. Okay. I may have to, in a moment, go get something to help clear my throat. I'm having a lot of drainage problems today. Earlier, students said probably the change in weather certainly is a change. And probably isn't being helped a lot by, for some reason, the room seems to be modifying its temperature. Like when I came in here after lunch, the room was quite chilly, and now it's almost too hot to be comfortable. You know, if you just went outside in the cold, it probably feels very comfortable, but it feels almost stuffy, and that I think it's driving my head crazy, you know, by those kind of changes. All right, we're just starting section 13.7. If you have, you don't have a book, but it's on page 931. All right, I just said this, but I'll go back and do a little bit more. Earlier, when we were doing the objectives, I wondered if it was correct or a misprint to have little f in one place and capital F in the other. I thought they were just representing a two-dimensional equation, or a two independent variable with little f and 3 with capital F, but these are connected. Okay, it says you've represented the surfaces in space primarily by equations in the form z is equal to f of x, y, where z is the dependent variable and x, y are the independent variables, say down on the x, y plane, determining what value z has on the perpendicular to that plane. Okay, in the development to follow, however, it is convenient to use the more general representation. This is where the capital F comes in. Capital F of some functions, x and y, but then counting z as if it's an independent variable rather than a dependent variable. And what you do is basically subtract that from f of x, y, and then make that difference your capital F vector function, and that then is a function of z as well, and that's equal to 0 because you subtract z from both sides. For a surface S given by z is equal to f of x, y, you can convert the general form to the general form, capital F, by defining capital F as little f minus z. And that's what I just said. That makes that capital F equal to 0. Okay. Now, it seems like a shell game. What's the deal with this? Why is that even important? Well, let's see if we get to that. Because f of x, y minus z, little f of x, y minus z is equal to 0, you can consider the surface to be the level surface of capital F given by f of x, y, z equals 0. Okay? If you then define that function up there to be your capital F, then the S is the level surface for that newly defined function. Okay? Okay. So here's example 1. Let's see if we can make a little more sense out of it with this example. For this function, capital F of x, y, z is equal to x squared plus y squared plus z squared minus 4. Okay? Now, that's a function, a generic, well, not generic exactly, but a function in 3 independent variables, x, y, and z. All right. Typically, that's not a surface. That's a spatial entity. In fact, we know exactly what that is, don't we? If you set this equal to 0, add 4 to both sides, what would that be? Second? No, if you set x squared plus y squared plus z squared is equal to 4. Set this equal to 0, which I don't do right down here. Add 4 to both sides, what figure would that be? X squared plus y squared plus z squared equal 4. It's a sphere of radius 2. Okay? Notice all the coefficients are the same. Okay. If one of these coefficients had been different from the other two, or all 3 of them different, but all pluses, that would be an ellipse. But with all the coefficients the same, that's a sphere. So, yeah, all the coefficients are the same there. So that would be a sphere of radius 2. Okay. Now, I guess that's exactly what we just answered. Describe the level surface given by that. We just did. Set that equal to 0, add 4 to both sides, you just described the sphere. Did you ever find it?
I haven't seen it yet, but the speech class is over there.
Oh, is it? Okay, so you're going to need this room then?
Yeah, I'll probably need this one.
Okay, all right. Are you going to use your computer or will you need mine?
I'll use that computer. I already got it set up.
Okay, all right. Well, then as soon as this class is over, I'll bug out rather than hanging around and doing things.
That means you have to use that computer. If you leave it there, I can use that one, so you won't have to keep, swapping it, switching it, taking it loose and all that.
Well, I need to take this to the Birmingham campus at 4 o'clock anyway because I'm teaching a class there.
So it works out.
Yeah. So you'll use that one?
Yeah, I use that one.
All right.
Okay.
If I see them, I'll tell them to wait here for you or go down to the lab.
Yeah, go down to the lab. Just feel open.
Okay. All right. So I think we just did describe the surface. I didn't mean to jump ahead of the problem, but I think that's all they're asking for. The level surface given by that can be written as this, which is a sphere of radius 2 whose center is at the origin. So that's the surface we're talking about, that sphere, radius 2, center of the origin. So yeah, that is the level surface. Now, if you had changed that and solved for z, okay, and make that your little f, then you would have had z is equal to four minus x squared minus y squared, the square root of 4 minus x squared minus y squared. And that would have been describing a hemisphere because it's just a square root, which would have been the same thing, okay? But they're not going back and doing that. All right, so that's a little bit on level surfaces, okay? Jumping now then, it says, trying to see, oh yeah, they leave off the first sentence that's in the book. You have seen many examples of usefulness of normal lines and applications involving curves. And then it picks up here. It says, normal lines are equally important in analyzing surfaces and solids. Remember, normal lines are the lines that are perpendicular to normal to the surface at any given point. For example, consider the collision of two billiard balls, okay? When a stationary ball is struck at a point P on its surface, it moves along the line of impact determined by P and the center of the ball. So if you hit it square on here, hit it square on here, this ball is going to take off in this direction. Okay? And it moves along that line of impact determined by P and the center of the ball. So if this point of impact is going right to the center of this ball, then this ball follows its center, goes right along this line of impact. The impact can occur in two ways. When the cue ball is moving along the line of impact, it stops dead and imparts all of its momentum to the stationary ball, as shown here. That's conservation of linear momentum and conservation of kinetic energy at the same time. Okay? When the cue ball is not moving along the line of impact, it's deflected to one side or the other and retains part of its momentum. So this time, here is the line of impact, and the cue ball is not moving along that line, but coming in at an angle. And if you've ever played pool, you know this is what happens. The pool ball recoils this way, and this ball moves this way. Okay? Now, it does, at least in their drawing here, appear that this is moving perpendicular to the line of contact, you might say. From the point of contact through its center, it's moving in that direction. And I've seen many pool players, they probably aren't the professionals, they may not do it, but they think they act like they're professionals. They'll go and line up exactly where they want to hit that ball, and do this, and then get the cue ball and try to aim it so it hits that particular point. And that's what it's doing, because it's going to be perpendicular to that, what I call the line of impact, the tangent line there, and it's going to go perpendicular to that, which is going to be a normal line. Now, what happens to the cue ball's direction, and I take it this is the initial line there, that it gets bounced off this way, and basically angle of incidence. So it's indicating that it goes in the tangential line where that was, the line that was tangent there, the cue ball follows that, and this goes perpendicular to it. If that's the case, that always makes that a 90-degree angle. I can't picture that with cue balls well enough to know that's always the case. Okay. The part of the momentum that is transferred to the stationary ball occurs along the line of impact, which is from the point of impact to the center, regardless of the direction of the cue ball. Okay? This line of impact is called the normal line to the surface of the ball at the point P. So that's what we were observing here. That is always moving perpendicular here to the point at the point of impact. Now, the illustration here says the cue ball then follows along up here, but down here it says regardless of the direction of the cue ball. Okay? I don't know which of those two statements wins. Okay. All right. In the process of finding a normal line to a surface, you're able also to solve the problem of finding a tangent plane to the surface. So the tangent plane must contain that normal line. Let S be a surface given by this good old expression here, alpha beta plus z is equal to 0. And let P of x0, y0, z0 be some point on that surface. Okay? Let C, capital C, be a curve on that surface S through the point P that is defined by the vector valued function, R of t is equal to x of t y I plus y of t j plus z of t k then for all t, the f, this capital F of x of y, x of t, y of t, and z of t is equal to 0. Okay, let's see. We've introduced so many new things. The statement here, let C be a curve on S through P that is defined. Okay, got it. This vector value function R of T is going to map out that curve C. That's what they mean. So these functions here of those various variables are the functions necessary to map out this curve C. So that's where the tie comes from. And then for all t, then this F, this one here, is going to be 0. Okay? Because C is on the curve, so if S is a surface given by that, C on the surface is going to be that. So with that, those values, that will be 0. Okay. Now, if F is differentiable, that's the capital F function, which is a function of x of t, y of t, and z of t. If that is differentiable, and the first derivative of x with respect to t, first derivative of y with respect to t, and first derivative of z with respect to t all exist, that means there's no infinite slopes or anything there. Then it follows from the chain rule that, okay, remember F, capital F is a function of x, y, and z, but they're all functions of t, so capital F is also a function of t, okay? And its derivative with respect to t would also have to be 0, okay? Because when you take derivative of this with respect to t, because this value is 0, is derivative. I think that's the reason it's got to be 0. Okay. Now, what is that derivative of F? It's the partial of F with respect to x, y, and z times the first derivative of x with respect to t plus the partials. This is the chain rule coming into play. Remember, F is a function of x, y, and z. Those are all functions of t, so the derivative of F would be the partial of this with respect to x times the derivative of x with respect to t, plus the partial of F with respect to y times the derivative of y with respect to t, going down the line there. Okay? So that's what this statement here is saying. That is what the first derivative is. Partial of F with respect to x, blah, 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 blah. Okay. Now, at that point, x0, y0, z0, okay, let's go back and remind ourselves at that point, that any point on that surface generated by that, this is any point on the surface, be a point on the surface, let's see, back up, and C be a curve on S that goes through that point P, okay? So if at this point P, the equivalent vector form for that thing is the gradient of F, that's this part here, dotted with the first derivative of R, and the first derivative of R is x prime I plus y prime z, j plus z prime k. So that would just be, those components would be meshed with that one in the dot product. Okay, so that gives you exactly that. But at the point x0, y0, z0, that's where you calculate the F, and over here is the R prime at the point where t is equal to t0, because that's how you get your p0 is, it's basically what you're having to do to your functions there is find the place where the first derivative is that. All right. Terrell is here. 10 o'clock scholar. Okay.
Yes, I am. Double the class up.
What's that?
So we double the class up. We're going to double the class up.
Oh, you don't know when the class starts?
Yeah.
I see. Okay. I have to review your schedule for you. Okay. So the t equals 0, x is equal to x0, y is equal to y0, z is equal to 0, 0. They never actually say that. I went back just to see if they did, and they don't physically say that, but that's usually what that nomenclature means. Okay? Now, think about what this is. The gradient dot product with the tangent vector, that's exactly what the tangent vector is at that point, at that t equals t0. And this tells you that the gradient has to be perpendicular to the tangent vector because that's the only way the dot product is going to be 0. Well, unless one of the other is 0, but I think we can safely say in general that's not the case. Okay. Seems like it's taking a long time to get anywhere here. Okay. This, I think, is, okay. That result that we just talked about means that the gradient at some point P is orthogonal to the tangent vector of every curve on S through P. So that all the tangent lines on S lie in a plane that is normal to the gradient at x10, y0, z0, which is the coordinates for P, and contains P as shown here. Okay. All right. Here's your surface. Whatever shape and size and dimensions and characteristics of that surface has. We do know that it requires for all the first partials to have values. You know, they can't be infinite or anything like that. Okay. The tangent line along any of these curves, this one looks like it's along that curve, is tangent to the surface there. But, any curve you choose, there is a tangent line that's there. And that tangent line has to be perpendicular to the gradient along each of those curves. Now, of course, the tangent line varies, its gradient, could be, let's see, that's not true. Because that gradient is fixed no matter which direction you come in, I believe. So, basically, the dot product, that gradient vector is normal to every tangent line at that point. But, almost has to be that way. I believe if they didn't just say, all tangent lines of S must lie in a plane that is normal to that gradient vector at that point P. Okay? Now, let F be, that's pretty weak looking F there, isn't it? Let F be differentiable at the point P, x0, y0, z0. On the surface S given by this function, f of x, y, z, capital F, is equal to 0, such that the gradient of that F at the point P, which is x0, y0, z0, is not equal to 0. The gradient can't be 0 there, okay? And remember, gradients are vectors, so it can't be the 0 vector. It can't have no magnitude there. The plane through the point P that is normal to the gradient at P, okay, is called the tangent plane to the surface S at the point P. And the line through P having the direction of the gradient is called the normal line to S at P. Okay, the line through P having the direction of the gradient vector at x, y, 0, x0, y0, z0. It's called the normal line to P, to S at P. That's right. So basically, that is also your normal line. I used to call it a normal vector. Okay, tangent vectors are always perpendicular to normal vectors, and all the tangent vectors here are perpendicular to your gradient, and therefore the gradient must be in the same direction as the normal. Okay, so that's basically what that line is saying. The line through P having the direction of your gradient vector at that point is called the normal line to S. There's one and only one. To find an equation for the tangent line, tangent plane to S at the point x0, y0, z0, point P, let x, y, z be arbitrary point on that tangent plane, then the vector, vector v, will be this coordinates of this this is just any arbitrary point on the tangent plane. So x minus x0, I, plus y minus y0, j, plus z minus z0, k, lies in the tangent plane. That vector does because it contains this point and that point in a line, okay, in those directions. Okay. Now, because the gradient of alpha x, y, x0, y0, z0 is normal to the tangent plane at x0, y0, it must be orthogonal to every vector in the tangent plane, every one in the tangent plane, and you have that the gradient of alpha at x0, y0, z0 dot that arbitrary tangent vector v, the dot product has to be 0, which leads to this theorem. Now let me make sure the last part I said correctly. I'm pretty sure I did. Yeah. Arbitrary point in the tangent plane. Okay. And that vector lies in the tangent plane. Okay. Here's the next theorem, 1313. Really lucky theorem, wouldn't you say? Equation of a tangent plane. Elf's really don't print out well. If F is differentiable at x0, y0, z0, you can't take a derivative there. It's not going to be infinity or anything. You can't take it. Then an equation for the tangent of the tangent plane to the surface given by F F of x, y, z is equal to 0 at x0, y0, z0. Okay, is, okay, F is differentiable there, and an equation of the tangent plane to the surface, tangent plane to the surface, here's what it is. The partial of F at x0, y0, z0 times your x minus x0 plus partial of y at x0, y0, z0 times y minus y0 plus the partial with respect to z at x0, y0, z0 times z minus z0. Third component of that arbitrary point we started with. Okay. Now, if it hasn't dawned on you yet, this gradient vector is a really powerful thing. It is the normal vector, or it's in the same direction as the normal vector. its components of that, or you get right back to the forget that last thought. I think we've already said it just by every way we can. So let's see what comes next. Here's example 2. All right. We're going to apply this now. An equation. Sorry. You too, huh? Find an equation of the tangent plane to the hyperboloid. This is your hyperboloid. At the point 1, -1, 4. Equation of the tangent plane to this hyperboloid at the point of that. Okay? Now, okay. My back is itching like crazy. I don't know the weather or whatever. All right. Back when you were doing, I can't think of a better way to say it than linear differential calculus, one independent variable, one dependent variable, your function, and one independent variable. What would you do if you said to find the equation of a tangent line? What would you do? First step, take a derivative. Okay, now we're going to find the gradient, which is kind of like in 3 dimensions, 2 or 3 dimensions, taking a derivative. Okay. All right. So that's going to be step 1. Well, okay, sorry. Actually, step 1 is to write this as your function. Now, have I not written anything yet that this came out red? I would have thought so. Okay. So let's rewrite this as your f, capital F, of x, y, and z. And say that's z squared minus 2 x squared minus 2y squared minus 12. Okay. Now this is the one you take the, you basically find the gradient of, okay? Though we're not going to quite write it as a gradient yet, we're just going to take the partials. So the partial of this f with respect to x, at x, y, and z, would be what? Partial of that with respect to x. A little louder? Minus 4x. Minus 4x. Okay? Yeah, you're right to do that. Okay?
What's the first letter of front?
Okay, I can't read.
What's that sign in front? In the first line.
What's what?
The first line you wrote. What's that?
This one?
Yes.
Okay. Here is the hyperboloid equation. Okay. Now write that as a function that's equal to 0. In other words, subtract 12 from both sides. So you take this, subtract 12 from it, and make that equal to 0. So this is your first function. That's your function, f of x, y, z. The capital F.
What's that first thing? Is that?
Up there?
Is that z squared?
Yeah, I think he's talking about the L.
Oh, the f?
No, the Z squared.
After the equal sign.
After the equal 2 squared.
Actually, yeah, that's z squared.
Oh, okay.
We're taking the
Z squared minus, yeah. And then just subtract 12 to make that equal to 0.
Okay, I see.
Yeah. All right,
I
so
wasn't sure
that's,
if it was z squared or.
what's that?
I wasn't sure if it was a z squared or what it is.
Yeah, it's a z squared. Sorry about that. It's ugly, I admit, but you're making fun of my writing. It's all right. It doesn't bother me any much at all. Yeah. I'm fine with it. Okay. Okay. A little better. Okay. All right. All right. What's your f sub y? The partial of f with respect to y, x, y, z. That would be minus 4y. And your partial of f with respect to z, x, y, z. Say again? 2z. Okay. Or not 2z. Okay. 2z. Now, take all three of those partials, evaluate them at the point of interest. Okay? So your f sub x, partial of f with respect to x, at this point, 1, negative 1, 4. Okay? That would be what?
We just plug in x, right?
Yeah. Just plug in the x. Okay. Actually, yeah, negative 4. You plug in the 1 for x and you get negative 4. F sub y, partial of f with respect to y, at 1 minus 1, 4, would then be positive 4. And the partial of z with f with respect to z at 1, negative 4, negative 1, 4, would be 8. All right. Now, neck is so stiff. Okay. What we're looking for is the equation of a tangent line to that hyperboloid at that point. Well, here's what that equation is. Okay? It's your partial of f with respect to x at that point. So that's going to be minus 4 times x minus 1. Okay, if you go back to the previous theorem, 1313, you do the partial at the point times x minus x0, where this is your x0, plus 4 times y minus y0, wait a minute, y plus 1, okay, because that is a minus 1, so it's y minus a minus 1, okay, plus 8, the partial with respect to of alpha with respect to z at that point, okay, times z minus 4, and that set that equal to 0. Okay? That is what your previous theorem told you to do. Okay? You could leave it like that, but that's not really a very handy form. Let's multiply through and see what you get. Minus 4x plus 4 plus 4y plus 4 plus 8z minus 32 is equal to 0. Okay? Okay. Having trouble separating my z's from my 2's, but that's a 2 there. Okay? All right. So let's pull out the variable terms. Minus 4x plus 4y plus 8z is equal to, and we're going to take all the constants and move to the other side. That will be a 32 minus 8, 24. Okay. I don't know if that's how they leave it or not. Is it? Okay? Actually, what they do is take that, which I've just written, only they didn't write it like that, and divide everything by 4, because that's a common factor. Minus x plus y plus 2z is equal to 6. Because you're dividing everything by 4. Okay, now they wrote it slightly differently. And there's no real reason why, except it's perfectly fine. They wanted to lead with a plus, so that would be x minus y minus 2z. And if you had moved this over here, that would have been a minus 6, but they're moving to the other side, making it plus 6 equals 0. Okay. Don't know if any reason. Well, you just multiply both sides of the equation. Yeah. It's an equation, you can do that. Okay. Or, if you want to do it this way, add x to this side, subtract y from this side, and subtract 2z from that side, and that would give you x minus y minus 2z plus 6 equals 0. Same thing. Or multiply. Either way. Okay. All right. That is the equation of a plane, and that plane happens to be tangent at that point, because those partial derivatives make it so it has to be, and using the equation of the hyperbolic hyperboloid, I'm sorry, the hyperboloid. Okay. This one happens to be a circular paraboloid, if I'm not mistaken. Hyperboloid. Because it's not, well, they are ellipses too, but the x's and y's have the same coefficients, so that would be elliptical in nature. Okay. Okay. Let's see how they do it before I move to the next thing. I think it'll be very similar to what I did. All right. Begin by writing that as the function capital F, which is subtracting this from that side, leaving a 0 on that side. That's the equation of the surface, it's called. This is the equation of the hyperboloid, and when you subtract the 12 from both sides and make it equal 0, that's the equation of the surface of that hyperboloid. That's just the way they use the nomenclature. Okay. Now, consider that to be your consider that to be your they had a name for it. The level surface, that's what I was trying to do, of F. The value would be the connected with the level surface. So that's the surface. Then considering that, to be your level surface, you have the partial of F with respect to x is minus 4x, partial of F with respect to y is minus 4y, partial of F with respect to z is 2z. Okay, and since we're doing wanting the equation of the tangent plane to at that point. Oh, and that's one thing I hadn't done. Yeah, I always like to do this too. I want to make sure this point is on that. If it isn't, it's not making any sense, is it? So let's see, when you plug in a 1, okay, that would be minus 2. Minus 2 would be, because this also is a 1, that would be minus 4. 16 minus 4 equals what? Yes, that is on there. I didn't do it to begin with, but I always like to make sure that point is on that surface. If it wasn't, the problem doesn't make sense, okay? So make sure it is on there, and it indeed was. You want to get yourself all tied up in a wad and realize the point wasn't even on there. You've been trying to prove something that can't happen. So also let you know whether you've copied it right or not, okay? So at the point 1, negative 1, 4, evaluate those partial derivatives that we just took back here. Oh, I guess I didn't do that, did I? Okay. We had done it. Considering this function here, then take the partial of that with respect to x would be minus 4x, with respect to y would be minus 4y, with respect to z would be 2z. Okay? Then evaluate those three partials at the point that you're interested in, at that point. So the partial at that point would be a minus 4 in the x direction, positive 4 in the y direction, and then plus 8 in the z direction. Really going high in z. Okay? So an equation of the tangent plane would then be this value at that point, okay, times x minus 1, plus this value, the partial with respect to y, at y minus 1, which would be y minus 1, with y plus 1, then plus that value, partial at that point, times z minus 4 is equal to 0. Okay? Now, that is an equation of the tangent plane. But it's not the simplest or easiest one to follow or see. So let's multiply through and see what we get. Minus 4x minus 4, plus 4, plus 4y plus 4, plus 8z minus 32 equals 0. That would be minus 4x plus 4y plus 8z minus 24. When you add 8 to this, you get minus 24. That's equal to 0. And then just divide everything by minus 4. Why not? Okay? Make it simpler. X minus y minus 2z plus 6 equals 0. All right. Now, let's use this picture to okay, now x is coming this way, y is that way, z is that way. So sometimes they shift this around and it doesn't look like it's in the right place. This is here's the point, 1 on x, 1 on x, minus 1 on y, and plus 4 on z. Yep, that's on that curve. Okay? Now, the tangent plane there, they've drawn here. This is the equation of it. Okay? And if you'll notice what that means, the partial in the x direction is negative. Okay? That's coming downhill in the x direction. Partial in the y direction is positive. And to me, I cannot see that on this representation. It doesn't look at all like that can be positive. And partial of this of your overall function with respect to z, that's the greatest of any, so that it should be along the z-axis should be the steepest. Frankly, it looks like to me along the x's and y's, they both seem to be negative, but it says x is positive and y is negative. But anyway, that's what you have there. Now, to find the equation of the tangent plane at a point on the surface, given by that, you can define the function capital F to be f of xyz is equal to little f of xy minus z. Okay? Then S is given by the level surface on that function f of z, x, y, and z. Okay. Let's see. And we just found the equation, so I'm not really sure why they're saying to find the equation of that. Okay. This is just repeating what we just did. And for the life of me, I can't see any real reason, except maybe now we're going to focus on what the z is. Then S is given by the level surface of that equals 0, which is just what we did. Theorem 13, the equation of the tangent plane to S at the point of that would be this. So this is just repeating everything we just did.
But is that the same theorem you just used?
No, okay. Here's the difference. Okay, sorry. Now I'm catching what the difference is. This time, rather than taking the partial of f with respect to these three, we're taking the partial of this f and derivative of z. Okay? So that gives you the partial of f with respect to x at x0, y0, times x minus x0. Just like before, was the partial of y with respect to this times y minus y0. But derivative of z with respect to z is 1. Okay, so that would be a minus 1 times z minus z0. And that's equal to 0. So that's done doing it on this side rather than that side. Okay? Now, and they just leave it there, okay? They don't do anything with it. Oh, they do too. They just left those off. Okay. Let's now do example 3. How are we doing on time? Okay, today, we can't run over today, okay? At 1:55, I've got to stop because Dr. Bryant, let me make sure this is still true. The speech class is left, so maybe we don't have to leave. See, the speech class had shown up and he came in to say, they're here, so that means we'll need to use this classroom. Now the speech class is gone, it looks like. Oh, there, what does it say?
They were in there when I was talking.
Speech 107. Something meeting. What's that first? Take note. Oh, Calvin King. Okay. Yeah, K. King meet in room 201, 1, 2, 3, 30 or whatever that is. Okay. So that means they're gone. Okay, so we don't have to. We can go over now. Yeah, I knew y'all would be happy. Okay. I'll try not to. Stop me if you. Before I was going to have you stop me. So let's do example 3. Find an equation of the tangent plane to the paraboloid. Z is equal to 1 minus 1/10 x squared plus 4y squared at the point 1, 1, 1/2. Okay. And again, this time I'll remember it on the front end. I want to make sure that point is on this paraboloid. So let's plug a 1 in here. And you get x equal 1 in 1 plus y equal 1, 4. 1 plus 4 is 5. 1/10 of 5 is 1/2. 1 minus 1/2 is 1/2. Yes. So that point is on that place. Now, it was raining like crazy not too long ago, wasn't it?
Yeah.
Look at that blue sky now.
Yeah, he said it's opening.
It's really pretty. Huh?
He said it's opening sunlight. No, it looks like.
Yeah. But it still almost looks like it's nightfall or something, because it's still really dark looking outside, even though you see some bright clouds and sky. That's strange. Okay. So anyway, what we want to find an equation for the tangent plane to that paraboloid. All right. Now, according to our last definition, this tangent plane is, now, just to get the idea, this thing right here is now what they're calling little f of xy. It doesn't have the z's on the other side. What they said we could do now is do the partial of little f with respect to x at 1, 1. Okay, we're not going to plug it in yet. Let's do xy first, xy. So what's that partial? Anybody?
It's what?
It's what?
You said what's the partial?
With respect to x. No, just at xy. The partial with respect to x at the values xy. In other words, take the partial of that in the circle, or that odd shape there, with respect to x. Minus 1/5 x. Got it? What's the partial of that with respect to y? Okay. Try one more time. 2 times 4 is 8y over 10. Oh, and you said fifths. Yeah, okay. Minus 4/5. Okay, I thought you were saying tenths. 4/5 y. Okay, perfect. Okay. Now let's evaluate that at 1, 1, because you don't need the 1/2 in there. So f sub x at 1, 1 would be minus 1/5. F sub y at 1, 1, you don't need the z in there, is equal to minus 4/5. Okay. Now, what you're doing is at the bottom of that page, okay, and this would be minus, the equation of the tangent line would be minus 1/5, your f sub x, times x minus 1 minus 4/5 times x, y minus 1, that's that one, and then minus that's always a minus, and guess what? There is no coefficient to it, it's just z minus 1/2. Z minus the z naught there. And that equals 0. Okay? It's exactly what we have at the bottom of the previous page. These two are pluses, but they happen to be negative values. The z is always a negative. Okay? Because you do f of xy minus z equals 0. And that's why that's always a minus z there. Positive for x, partials of f and x, f and y, partial for f at x and y, but these just happen to be negative values there. Okay. Now, let's clean that up a little bit. And how I want to clean it up, if it's okay with you, is multiply everything by 10. Is that okay? That gets rid of my denominators. So this will be minus 2. Let's multiply it by minus 10. Is that okay? Yeah, make it positive. That would be 2x minus 2 plus 8y minus 2 minus z plus 5, minus 5. Wait, no, it's plus z minus 5. Keep forgetting which one I'm subtracting, okay? Equals 0. Okay, let's see if I did it right. Let's get our constants, our variables together. 2x plus 8y plus z equal to 9. Minus 2, yeah, and that'd be a minus 9 on this side. Okay, and I forget, they don't do that. Sorry about that. And they didn't get rid of their denominators, and they didn't get rid of their minus signs. What a pain in the neck. Okay, so let's go back and redo it the way they did, just to make sure we got the right thing. Minus 1/5 x plus 1/5 minus 4/5 y plus 4/5 minus z plus 1/2 equals 0. And that would be minus 1/5 x minus 4/5 y minus z. Oops. And then they do plus 5/5 plus 1/2 would be 3/2. Is that what they got? Yes. Okay. I like mine better, but both of them are equations of the tangent plane. Okay? I don't like all the fractions personally, but we can live with it if we have to. Okay. Now, they have a little statement next. The gradient del capital F, okay, provides a convenient way to find equations of normal lines as shown in example 4. Example 4 is also at larsoncalculus.com for an interactive version of that type of an example. So, let's clear all this. Any questions on this before I clear it? Okay. Okay. Find a set of symmetric equations for the normal line to the surface. Here's the surface. X, Y, Z is equal to 12. Okay. Now, before we do, at the point, 2, -2, -3. Okay. Time out. Let's check and make sure that point is on this curve, this shape. 2 times -2 would be -4 times -3 would be +12. Yes. So that is on there. So that's a legitimate request here. Okay? Now, first thing we're going to do is write this in terms of capital F, which would be capital F of X, Y, and Z would be X, Y, Z minus 12, because that's equal to 0. We just subtract 12 from both sides and get it equal to 0. Okay? Now, find the set of symmetric equations for the normal line. Well, the normal line is always parallel, you might say, or in the same direction of the gradient. So all you have to do is take the gradient of this F. Okay? So gradient of f, and that is a vector quantity. I always like to put the vector symbol over it. In the book, you might note they make it a bold-looking del, which tells you that is a, but that's sort of hard to do. Del f at x, y, and z is equal to what? Remember what the gradient is? Generically? Well, I'm going to use a simpler notation. Partial of x with respect to xi plus partial of f with respect to yj, if I could write, plus partial of f with respect to zk. That's what your gradient vector is. What is your partial of f with respect to x? F sub x. Partial of f with respect to x. Remember how to take a partial?
I was just taking the
What's that? Okay. Okay, one more time. Derivative with respect to x, holding the y and z as if they're constants.
Oh, so you'll have
What would that be then?
L of x and yzi.
That would just be yzi. You're absolutely right.
Now y is
xzj, xyk. Perfect. Okay? Now, at the point in question, we're going to, that point right there, we're going to just plug in those values. So that would be what? What would that be? 6i minus 6j, right? Okay. Minus 4k. Okay. Now, it says find a set of symmetric equations for the normal line to the surface at that point. Okay? This whole thing has direction numbers 6, minus 6, and 4. This whole thing's about symmetric equations. We didn't actually do anything with those. This must be coming from a much earlier chapter, and frankly, I remember a little something about it, but not. Let's see, symmetric. What do they mean by that? Let's see if we can find that. Symmetric equations, line in space, 787. Okay. If you go back, any of you got books, 787, Theorem 1111 says, a line L parallel to a vector V, which is ABC, passing through a point P, which is x1, y1, z1, is represented by the parametric equations x is equal to x1, which is from that point, plus at, y is equal to y1 plus bt, and z is equal to z1 plus ct. If the direction numbers a, b, c are all non-zero, which in our case they are, then you can eliminate the parameter t, okay, that's where it comes from, in the parametric equations to obtain symmetric equations, and that basically is just saying that x minus xi, x1 over a is equal to y minus y1 over, okay. So basically what we say then, this is our a, b, and c, okay? And so you say x minus 2 over 6 is equal to y plus 6 over, no, y plus 2 over 6. I got them in the wrong place. Y plus 2 over 6 is, equal over a negative 6 is equal to z plus 3 over a negative 4. Okay? Yeah. And those are your, it said, find the set of symmetric equations. There they are. Okay? Yes?
I'm sorry to interrupt you.
No problem.
I need to show you this.
Okay. Who's that from?
Dr. Wilson.
Oh, Dr. Wilson. Yeah, the only thing I had a question about was Darlene said start the classes at 8.
Okay.
And, you know, normally classes start at 8:30. So
Yeah.
I just wanted to make sure that was okay. But in addition to that, because they're longer classes and they meet 3 days in their mini terms, Darlene already has a class starting at 9:45, and this one would be going from 8:45 to I have it all down in my office. Let's see. It would be going, okay, it would be going 8 to 9:40, and then her next class would start at 9:45. That would be okay.
Okay.
Okay, 8 to 9:40.
Okay,
and
excuse
then
me.
her next, so she only has 5, so tell her they have to be 8 to 9:40.
Okay. I'll let
Okay,
her know.
yeah.
Thank you.
I saw it yesterday, but I didn't have a chance to respond to it yesterday.
I
I was
understand.
going to do it
I
today.
think she's just trying to get them in.
Right, okay.
Thank you. Sorry to interrupt.
No problem. Okay, we just recorded all that. Okay. I hope I'm thinking right. I don't have the paper in front of me, but I believe that's it. Okay, so those are your, what they call the symmetric equations. You have to go back to where I was talking about, and you'll see that's how we set it up. The x minus 2, y minus or minus 2, z minus or minus 3, and you divide it by the what they call the direction numbers, 6, negative 6, and negative 4. And that's what it is. Where those come from are the parametric equations that they came from. X is equal to x is equal to 2 plus 6t. I think that's right. And y is equal to minus 2. Yeah. You get it from those parametric equations. Eliminate the t, and this is where those come from. That 2 is a bit weird there. Let me see if I can correct that. Okay. those are the equation. Now, frankly, I don't like having minus signs in the denominator, so I would have written that as minus y plus 2 over 6 is equal to z plus minus z plus 3 over 4. But that's just my preference. I don't like the minus signs down there. I like them in front, but whatever. Okay. Now, they show a picture in the text. We don't have it in our slides. I did not know what that surface looked like. It's a weird looking thing. And at the point 2 on x, they do these so strangely. I would have never figured that point was 2 on x, not the way they've drawn it. Negative 2 on y, yeah, that kind of makes sense. And negative 3 on z, I could almost kind of see that a little bit, but that 2 on x, that just looks totally out of place there. Okay, but anyway, I can't draw three-dimensional, and it's hard enough on a flat screen to interpret a three-dimensional, so that's what the difficulty is. Oh no! Is it that time? All right, we're going to have to start next time at example 5. Let me give you a few homework exercises here. We almost finished the section, not quite. Do either 3 or 5. They're both at Calc Chat, 5's at Calc View. Do 7, it's at Calc Chat and Calc View, and then do any of the odds 9 through 15, they're all at Calc Chat. Then do any of the odds 17 to 25, they're all at Calc Chat, 19's at Calc View. Do any of the odds 27 to 31, they're all at Calc Chat, 27's at Calc View. Do either 33 or 35 or both, they're both at Calc Chat, 33's at Calc View. Wait a minute. No. Stop, don't do 33. We haven't gotten there yet. Stop at 31. All right, we'll pick up the rest of those next time. Oh, and y'all do know about the bad news, good news, bad news situation, right? Yeah, isn't that sad? Yeah, get over it. Okay. Yeah. We'll see you next Wednesday. And then the even sadder news is Thanksgiving coming up awfully soon. And y'all get the whole week off then. That'll really be tragic. Yeah, we have to be here Monday, Tuesday, and Wednesday, but you don't. All right, I'll remember that attitude next time I grade your test. Okay, good deal. All right. Have a good long weekend.